Hello, welcome. Let's do a little introduction into the topic movement of forces. This is episode 31 of the series we are doing on static mechanics. All right, so the movement of a force about a point is defined as the product of the force and its perpendicular distance from the point from that point, or we can just say that it is the product of a force and the perpendicular distance to the line of force. So basically, what are we saying? The moment is just the force given, which is being applied, times perpendicular distance. And the unit of force is Newton. That of the distance will be in meters. We have centimeters and so on, but we are going to pick the meters to have it to be Newton meter. So a moment is simply the force times the perpendicular distance, which can be demonstrated in this form. So it is basically on moment on rigid bar or rigid bodies. So if this is a rigid body and this is being fixed or it is being placed on a particular pivot, then if a force is applied here, either upward or downward, that force that is applied so this is the line of action, and this is the point. So we are turning it at the axis here. We are going to just multiply the force applied, either it is downward force or upward force. So we are going to have our moment equals the force times the distance. The distance to be perpendicular to the force. So if the force is even moving up, the distance will be perpendicular to it, will be multiplied by that. You have for force times that. Now, in some cases, the force that will be applied to the one end of the rigid bar is not going to be perpendicular to the surface, but rather it will be inclined. So when a force is inclined, how do we get the distance to be perpendicular to the force? Because it is no more vertical, so it is not inclined at right angle. So it is inclined in this form. So what do we do? Then the force is, if the force is inclined at an angle theta, then the component of the force perpendicular to the distance is what we are going to use in finding that. You can see this is the force. Here, it is moving in this way. If we ignore the broken line, we are going to have this distance. And this distance is here. It is not perpendicular to the force being applied. So if we introduce this line upward, it will form an angle that are vertically opposite. And if we start from the point of origin and draw a line which is perpendicular to that, then it means that this place is going to multiply the force. This is the perpendicular distance we are looking for. So this perpendicular distance here will multiply the force here. And how do we get that value? Let's see if we are labeling here as x. And this is the part opposite to the angle theta, right? And this is also the part facing the hypotenuse, facing the right angle box, meaning this is the hypotenuse, this is the opposite. So I can find the sine of the angle theta equals to the opposite side over the hypotenuse. And if that is done, we are looking for the x. So we multiply both sides by d. If you multiply, d will come here, it will cancel here. So x will just be d times what? The sine theta. That is what we are going to have. So this area will be d times sine theta. We are not looking for this. This is the force we are looking for. So now the force is now perpendicular to this distance. So our moment here, our moment is going to be the force, which is going to be F, multiplying the perpendicular distance, which will be d sine what? Theta. I guess you can check that. This is the force times the perpendicular distance. In this case, the perpendicular distance is not directly displaced because it is inclined. So this is a different approach when the force is perpendicular to the distance, directly perpendicular. This one is not perpendicular, it is inclined. So we deal with this. Now let's see if we can put some values to the forces and see how that can be calculated. All right, so let's see if a question is given in this form, just to text what we are having, that the distance from the fixed point or the axis and the line of action is what, 30 meter, and the force applied at the end here is 10 meter, and we are asked to find the moment. So the moment will just be the force times the distance, which is going to be force 10 Newton. The distance is what? 30 meters. That will just give you what? 300 Newton meter. So this will be the moment, which is the turning effect force. The turning effect force that is applied in this rigid body. Now, if the force applied is inclined, as in this nature, what do? We are aware that your moment is going to be the force times d, the sine of the angle available. So in this case, what do? The force is going to be 70 times the distance, which is going to be 15, times the sine of the angle, what? 60 degrees. What do we have? 60, we have 0, 30, 45, 60. So we have the root 3 divided by what? 2. So if root 3 divided by 2, we know, let's multiply this and see. We have 70 times 15. We can make it 7 times 10 times 15. So we know 7. We'll multiply this as 105 times 10. This is what we are going to have. Then the 2 in there will divide this to give you 2 here, 5. 2 will go here, 2, 5. So our answer is going to be 5, 2, 5, the root of 3 Newton what? Meter. We can write this also in decimal, but just to show the multiplication aspect of a force that is what? Inclined. All right. Now that we have this out of the way, we know forces, any equilibrium that you have, there are so many forces that act on a body in different directions. So it means that the force that can be applied to this rigid bar cannot be only one force. It could be several forces. Then we need to talk about some principles that will govern us when we have various forces applying on a rigid bar. When a beam, something like this, is in equilibrium under the actions of several forces, not only one force, the sum of the clockwise forces of all the forces about a point. So you identify the point, then and locate those forces that are going in the clockwise direction, all of them is equal to the sum of the anti-clockwise moment. Here we are talking of moment, not forces, moment. Of all the forces about the point, the same point. So let's see, if we are having this beam and we are having a pivot here, and if I apply force here, we can see that this beam will either go down or go down this way. Let's take it. It will either go this way or it will go this way. If it is going this direction, as we are seeing this way, we will be talking about clockwise what? Direction. If it is going in this direction, that's what? Clockwise direction. If it is going in this way, as in this direction, we have what? Anti-clockwise what? Direction. Right? R, W, okay, anti-clockwise. Now, so the principle is saying that all the forces going in the clockwise, all the moments, the force and its distance give us the moment. So the sum of all moments in the clockwise direction should be equal to the sum of all moments in the anti-clockwise direction from that point. So here, if I want to look at clockwise what? Movement. Let's say clockwise movement is going to be the force that is applied times the perpendicular distance between them. What is the force in the clockwise direction? The force is Q. What is the distance? Perpendicular distance is what? The Y. So I should be having Q times what? Y. Then looking at for the anti-clockwise movement is going to be, I am having the force being applied here, which is having a distance from the fixed point, the point we are having as the pivotal point, is what? Perpendicular to the force P, and that is what? X. So P as the force times what? X. So we are saying that by the principle, if you are going to look at the principle, we are saying that the clockwise forces, which is going to be Qy, should be equals to the anti-clockwise force, which is what? Px. If you find the moment, so the moment of the clockwise forces, the sum of all of them, we can see only one force moment moving in the clockwise direction. One force moment moving in the anti-clockwise direction. So that gives us the principle being applied here. Now, if you look at this is also having the same rigid bar, but the forces are applied as what? Different places on the beam. So we can see that we can apply the force here, we can apply the force here. This is more or less like the ideas we use in turning or opening knots using spanner. If you have a spanner and you want to tie or unloosen a knot, wherever you hold, the distance that you are holding away from the knot determine the kind of turning effect you are going to have. If you hold far away, you need, the distance is long, you need some small force to operate on the turning effect. But if you hold it closer, it means I can also hold it closer to where the knot is and try to open it. That means that the turning effect, we need greater force. So here we are applying forces on different level of the beam. What are we going to have? This is also going to be the clockwise direction, and this is going to be the anti-clockwise direction. So let's look at first the clockwise moment. What are the clockwise movements here? If I look at Q, if I press Q, if Q is moving down, it's moving down with what? Its distance. So the movement is going to be this as the distance times the force. But W will also move in the same direction as Q is going. So it means both W and Q are moving in the clockwise direction. So the first force is going to be Q, the distance will be Y. So Qy plus the second force is W multiplied by what? The distance T. So the sum. So let's say the sum. Okay, this is the sum of what? Clockwise. Let's see it here. Let's put this one at this place as anti-clockwise direction. So as you have sum of clockwise direction. All right. So if I find a sum, I am having all these of them going downward. Good. Let's see sum of anti-clockwise direction moment. You can see this is also P moving along with its distance from the pivot Z. So I will have P times Z plus R is also moving in the same direction with its distance R and what? S. Good. So we know the sum of the clockwise moment. We also know the sum of what? The anti-clockwise moment. What do we need? By the principle, we can only say by the principle we know the sum of the clockwise moment will be equals to the sum of the anti-clockwise. So as we're having Qy plus what? WT should be equals to PZ plus what? R what? X. So this is what you are going to be facing if you are dealing with four forces acting at different places on the beam or on the rigid body. Now, you can be given some of them and some will be left for you to find. That is the beauty of showing the sum. This is in the equilibrium. So the sum of the clockwise equals what? The sum of what? The anti-clockwise. Now, there are some cases whereby there will be a normal reaction. There will be some forces moving upward on their own and some forces moving downward. How do we find the clockwise movement and the anti-clockwise movement of such beam conditions? Let's check it out. Okay, so let's look at this carefully. You can see this is also the rigid bar, as we can see, having four forces just like we have here. Force 1, force 2, force 3, force 4. 1, 2, 3, 4. But here all the forces are acting downward. Here, force 4 and 3 are acting downward. Force 1 and 2 are acting what? Upward. How do we resolve or find their resultant clockwise movement or the anti-clockwise movement? You can see if this bar is here and we apply forces here, holding down, this is going clockwise. So as the force 3 is going clockwise, the force 1 is also going clockwise. It's moving in the same direction. So I can say this is going to be clockwise direction, and this will also move in clockwise direction. The board is not big to write every word, so bear with me. Clockwise. So if I am going to press the force 4, which is moving in the anti-clockwise direction, the force 2 will also move in the same direction. So this is going to be anti-clockwise what? Direction. This is also going to move in the anti-clockwise what? Direction. So what do? We can resolve resultant. Let me make it that way. So the resultant clockwise moment. So the moment here, moment at force. Let's begin from here. See, it's 1 and 3. You see, this is clockwise. The force 1 is moving with the distance to be x1. Therefore, I'm having the force 1 times what? X1 plus the next one, which is also clockwise. That will be the force 3 times each distance perpendicular to the force as what? 3. Then we look for resultant. So the resultant anti-clockwise movement. Anti-clockwise. This is moving with the distance F2. So I have F2 with X2 as the distance plus which one again? The F4 is also moving. So F4, the distance is what? 4. So we can say that by the principle of moment, we can say that sum of the clockwise, which is F1 X1 plus F3 X3 should be equals to F2 X2 plus F4 X4. So we can see that there are about 10 cases that we are having in this case, whereby we have the forces all moving in one direction, as you can see. So we have one clockwise moment, one anti-clockwise moment. When the forces are exerted on several positions, it will not mean that it will be two all the time. It could be 1, 2, depending on the weight, the mass of the force being applied. So we can see that the clockwise, see, they are all acting downward. The clockwise is going to be all of them here. The anti-clockwise, I think clockwise will be all of them here. The anti-clockwise this way. But in the case that they are in opposite direction from one side, downward, upward, this becomes the way we can find the moment about a point as the pivot. I guess the concept is a bit okay. The video is a little bit long, so I will not add any more examples. The subsequent episode we pick examples to buttress the concept we develop in this episode. I believe you will watch to the end, share, like, subscribe, and leave a comment.